Now let us state the experimentally observed relation of the alternating stress to the number of cycles to failure. So what we're about to draw is called the SN curve, and here S stands for stress and N stands for life. Okay, so we're gonna have a plot in which the horizontal axis is going to be number of cycles to failure. So what is important is that that axis is always log scale. The vertical axis is not necessarily always linear. Sometimes it is log, but in most cases it is of linear form, so it's non-log. And I'm just going to write the dimensions here, usually just MPa. So it's non-log or linear scale, and that is the alternating stress or the stress amplitude, which is, remember, going to be equal to the nominal stress, because presently we're looking at a case where the stress concentration is 0 or the stress concentration factor is 1, and remember, we're looking at completely reverse loading, so it's important to keep in mind that the mean of the stress is also equal to 0. Sigma m or Sm is equal to 0. Okay, so now let us now depict the data. Well, what the data does is the following. First of all, you prescribe a certain stress amplitude, and then you start with a specimen, and then you just count the number of cycles until failure occurs. When failure occurs for a given stress amplitude, you have a certain number of cycles. So this is the number of cycles to failure, NF. Alright, now because this is a logarithmic axis, just keep in mind that the values are going to increase very rapidly. So this is 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6, 10 to the 7, 10 to the 8, etc. So we have a very rapidly increasing number of cycles to failure on the log scale. And so we've prescribed a certain stress amplitude, and we've counted the number of cycles to failure. And we do that for many different stress amplitudes, so we collect data. And the data, it turns out, looks roughly like this. So it's partially motivated by the kinds of plots that you can see in the book itself. So I encourage you to, at this stage, actually have a look at the type of data that one observes. Of course, there is always scatter in experimental data, and there can be considerable scatter. So let's say that's what the data looks like. So now what we would like to, of course, normally do is we would like to fit a model to the data. We'd like to fit a model usually because it has advantages in terms of design and analysis. So the fit is our model. And the fit could be a line, let's say, that looks like that. Okay, so now that's our fit, and here what we have, or what we will be eventually able to predict with the model, is for a given for a given stress amplitude. Okay, let's say, as an example, let's say this is 200 MPa. Okay, so we impose sigma A or SA equals 200 MPa, and we count the number of cycles to failure, and let's say it's over there. This would be the fatigue life at 200 MPa. Okay, so when one says the fatigue life associated with a certain stress amplitude, one is referring to the number of cycles to failure for that given stress amplitude. Okay, and we can determine that directly from our model if we have one, or we can look at the data. Alternatively, we might be interested in the stress we can apply to reach a certain life, in this case, say over here, close somewhere between 10 to the 4 to 10 to the 5 cycles. And so this value would eventually be the fatigue strength at, say, if this is 8 times 10 to the 4, I don't know exactly what that value would be, but let's say somewhere between 10 to the 4 and 10 to the 5, for instance. So if that's 8 times 10 to the 4, then this would be the fatigue strength of the structure or the material for that given number of cycles. So the fatigue strength and the fatigue life are two terminologies that we have to get accustomed to. Now, well, how does the data proceed? First of all, let's also discuss that. Now, we have a model, and let's therefore, from this point on, let's discuss in terms of a relatively nice smooth line. Of course, I could go ahead and draw the data points, but the lines are going to be, or the models are going to be representative to some extent of the data, well, to within certain fitting approximations. But eventually, the black line can, it turns out, proceed in one of the two different ways. One way to proceed is as such. So the black line proceeds, and it turns out that it levels off towards a certain value. Now, that value, in other words, we seem to observe that if the stress amplitude is below a certain value, okay, below that value, then you never get fatigue. You can cycle forever, okay, and you're not gonna experience the structure breaking, right? So, because you don't essentially have any data point for failure below that value of the stress. That value is called the fatigue, or sometimes the endurance limit. And associated with that E, it's usually called either SE, or in this case, SE is equal to sigma E. It can be called sigma E. Now, this plateau that occurs where the stress essentially levels off occurs usually somewhere after 10 to the 6 cycles, which is a lot of cycles. So if there is a fatigue or endurance limit, usually you observe the plateau after about 10 to the 6 cycles. Now, is this surprising? Is it surprising that below a certain stress amplitude, we do not observe fatigue of the structure? Not really, because remember, we've also observed something similar to this in the case of crack growth. In that case, we had observed that if the range of the stress intensity factor was below a certain value, which we called the threshold value. So remember crack growth, and what you should be really remembering is the threshold value. If the stress intensity range was below a certain value, then the cracks sometimes do not grow. There are such materials. Now, because fatigue ultimately has to do with the initiation, growth, and merging of cracks, it turns out that similarly, there is a certain stress amplitude below which the cracks just don't grow enough to cause fatigue at least reasonable number of cycles. So this curve levels off to almost a horizontal appearance. Now, does this always happen? No, just like you don't have always a threshold value, you don't always have also a endurance limit. So sometimes the way this curve goes is it just goes on like this forever, okay? So there is no limit sometimes. Now, even if there is no limit, sometimes what one says is that, well, practically number of cycles beyond 10 to the 7 or 10 to the 8, somewhere in that range, is already very, very large. So in some applications, if you design so as to ensure that you can reach 10 million or 100 million cycles or beyond, then that's as if you have practically an endurance limit, because fatigue does not become a concern then. So if you can ensure that eventually your stresses are low enough to deliver stress lives that are so large, and if you can ensure that your stresses are in fact even larger than the values that would be achieving such high stress lives, high fatigue lives, then it's practically a fatigue or endurance limit, because fatigue would not be a concern. So sometimes a practical endurance limit is the strength, is the fatigue strength at somewhere around 10 to the 7 to 10 to the 8 cycles. Okay, maybe a little bit more. So that would be a practical endurance limit. But in some cases, as we said, one does actually observe a physical fatigue limit. Now, in such cases, one might also be interested in modeling what that limit is. And it turns out that this limit is somewhere in the range of 0.35 to 0.5 times the ultimate strength of the material for many different types of metals. Okay? For many metals. On the other hand, if you just want to, if you know that there is an endurance limit and you don't exactly know the value, so the value might be stated in tables of material properties, but you don't know exactly what it is, but you want to guess what it is, a good value to start from would be half of the ultimate strength. This is a good guess for, let's say, either accurate or quick back of the envelope calculations for most steels. So for most steels, there is an endurance limit, and that limit is approximately half the ultimate strength. Okay, so let's keep that in mind. All right, so what we've discussed so far is the nature of the data. So there is some distribution that is not necessarily trivial looking, and sometimes the way that distribution looks is it displays a fatigue or endurance limit, and sometimes there is no limit. Either way, we understand that 10 to the 7 to 10 to the 8 is usually a very, very large number of cycles, which might in practice also act as a practical endurance limit for your design. Now, having said all of this, well, we're going to talk about, as we said, high cycle fatigue. And so what is exactly high cycle fatigue? Now, high cycle fatigue is something that is a little bit fuzzy. Now, it turns out that somewhere in the range 10 to the 2 to 10 to the 4, in other words, 100 to 10,000 cycles is where, and it lies somewhere over here, right? Is where one says that you have high cycle fatigue appearing. So it's not exactly a very precise number. One doesn't say that, okay, beyond 10 to the 4, 10 to the 5, you talk about high cycle. It could be that 10 to the 3 is also high cycle for the type of application you're seeking. So the transition is sort of a fuzzy region. So there's a fuzzy transition from what we call low cycle fatigue to high cycle fatigue. Okay. Now, high cycle fatigue is characterized by stresses that are, as you see from the plot, if you want to reach higher lives, then you have to decrease the stress amplitude, so we have lower stresses. And when the stresses are low enough, in fact, you don't observe significant, of course, plasticity, or in fact, perhaps there is none. Okay, so it's predominantly elasticity that we want to really talk about. Whereas in the case of low cycle fatigue, the stresses might be so large. Remember, if this is half the ultimate strength, then the stresses we're talking about here are actually very close to those values, probably well beyond the yield strength of the material. So here, what we're talking about is high stress, which have to do with probably significant plasticity, at least some appreciable amount that you cannot safely omit. All right, so this is the picture that we are going to look at. This is the ascent curve, and we're eventually going to try to model the ascent curve. We're going to try to model these lines, in particular the blue line. Now, high cycle. Now, what we see from this picture is that if you have 10 to the 6 cycles, it's probably going to be certainly high cycle. If you have about 5 to 10 cycles, as we observed with the paperclip experiment, then certainly a low cycle phenomena. So we're in the high cycle range. Now, 10 to the 6, is that a practical value? Well, it really is, because if you calculate the RPM that your engine runs at, and if you think about the number of hours it takes to drive, say, from Ankara to Izmir at RPMs that are certainly going to be beyond 1000, you can easily see that that drive is going to take of the order of 10 to the 6 or a million cycles in the operation life of the engine, just one trip from one city to another. So 10 to the 6 is not actually a very, very large number for some cases. So if you really want to make sure, right, that you can do many, many trips, use that car for many years, you'd like to make sure that your stresses are low enough and hopefully below the endurance limit, so fatigue is not going to be an issue. So I need to be able to model the fatigue behavior of the material so that I can design appropriately and achieve the desired lives. Right, so that's the general picture, and now let us therefore talk about design and modeling.